Hey learners, Jared here, and today we're going to look at an overview of direct current circuits. That is, circuits that are operated by a battery. And we're going to be looking at specifically resistor circuits. When making a direct current circuit, there are a couple of things you need to keep in mind in order for your circuit to actually work. First, you need to make sure that your circuit has a complete loop for the current to take. That is a one full circular path from the positive terminal all the way around to the negative terminal. The other thing to keep in mind is you do not directly connect the positive and negative terminals of the battery to each other. That will burn out your battery and can present a fire or shock hazard, and it's just not good. Don't do it. Now, when looking at a current, you can look at that current flow a couple of different ways. One way is a conventional current. That is, you imagine that current moving from the positive terminal of the battery around the circuit and then ending up at the negative terminal of the battery. The other way you can think of it is electron flow. Now, electrons we know are negatively charged, and that negatively charged electron is going to seek out the positive terminal. So conventional current and electron current flow are actually opposites of each other. Funny thing is, it doesn't really matter which way you imagine the current flowing, just as long as you're consistent in doing so. Whether you want to imagine electron flow or conventional current flow, it doesn't really matter in terms of analyzing the circuit. Other factors when analyzing a circuit are resistors. Now, what is a resistor? Well, it's something that impedes the current flow in order to generate heat. It can generate light. It's something in the circuit that you're going to use the current to actually do something. Now, a common misconception people have about resistors is that they imagine that the current slows down right there in the resistor and then it speeds back up once it gets through that resistor. Current flow is a lot like traffic flow, where you can only move as fast as the car in front of you. Well, if cars are slowed down in front of you there, well, then it slows down the entire loop. And so they can't speed back up because there's more electrons in front of them. So placing a resistor inside the circuit slows down current in the entire circuit. It's not just inside that specific resistor. Now, how much resistance there is, well, that depends on how your resistors are arranged. And there's two ways that you can do that. You can arrange them in series, so it's one after another, after another, after another. They're directly connected to each other. That's a series connection. Another type of connection is a parallel connection. There's actually a branch. There's multiple pathways for that current to take. And the two affect current in different ways. So let's first look at a series circuit. When evaluating a series circuit, you're trying to figure out the overall resistance for that circuit, or what's sometimes called the equivalent resistance. In other words, if you had all of these resistors and you wanted to simplify it down to just one resistor, what would that be? That's the equivalent resistance. When there are series connections, it's really straightforward to figure out the equivalent resistance. All you do is add this resistance plus this resistance plus this resistance. All of the resistors that are in that series circuit, just add up their resistances, and that will tell you the equivalent resistance. Now, how that series resistor affects the current, it's kind of like a checkout line at a grocery store. Imagine you have a checkout line that you go through and you take your items through, but you don't actually pay there. Then you have to go to another checkout line, and then you pay at that one. And then you go to another checkout line where they actually bag your groceries. And then you go to another checkout line where they try and get you to sign up for their credit. It just sounds like a nightmare, and it would really slow you down getting out of the store. That's what series resistor circuits are like. It's like a checkout line and another and another and another, and it's going to slow down the overall traffic flow of the circuit. Parallel resistor connections work differently. There are branches between, there are options that you can take for the current to have. And the current won't just take one or the other. The current will try and move as efficiently as possible. So it will fill both or all three or all four branches of a circuit in order to maximize the efficiency of that current flow. To figure out the equivalent resistance for parallel circuits, you actually take the reciprocal sum. That is, you add up 1 over that resistor plus 1 over the next and 1 over the next. And then you take the reciprocal of both sides to actually figure out the equivalent resistance. It works in exactly the opposite way that series resistor circuits works. More series resistors means more resistance. More parallel resistors actually means less overall resistance. Again, think about the checkout line. Imagine instead of just one checkout line to go to, there's 50 checkout lines. Well, now everyone in the store can get out of the store faster. There's more open lanes to go through, and overall traffic out of the store will increase. Now, how to determine how that resistance affects how much current or how much voltage is being dropped at that particular spot, we're going to need to look at Ohm's law to analyze those particular circuits, and that's what we're going to look at next. Hopefully I see you there, and as always, keep learning.